So today we're going to move forward with this model that I've been working on for many years now, and which I loosely refer to as the Ohm particle for obvious reasons. The yin-yang symbol, of course, is an ancient symbol with various meanings associated with it. And at first, when I used this figure as my muse, as my model, it was a little bit as a joke. But then, as I started to study this further, I realized that I could actually apply it to physical constants and get something that makes sense. And so I'm going to, in this video, I'm going to bring you through my logic, and hopefully by the end of it, you will have an idea of why I think this figure is special and why that it may in fact be a nice model, a nice schematic to describe particles, and in particular the mass of particles, why particles have mass, can be explained using this model. But before I do that, I want to point you to a model that was developed by Robert Distinti, and so this was the model that actually got me moving on my model here, because his model is actually very similar. So in his model, this is his model of the electron. In this model, he's got two charges separated at a distance. But for the electron, he's calling this Q1 and Q2, but they're both negative charges. And in my model, they are, I'm assuming it is a vortex-antivortex pair, particle-antiparticle pair, an electron-positron pair, however you want to see that. And so that's where our models differ, but he still does something really interesting, which I'm going to do, which I'm going to replicate, only I'm going to do it a little bit differently than the way he does it. So first of all, I want to point out that he's using the same mass equation that I'm using here, okay, which I'm showing right here, and only his Km, his magnetic constant, is my mu1, which is exactly 1 times 10 to the minus 7. He's got a Q1 or QS and a QT, which is Q source and a Q target. So he's assuming that they're sources and targets. In mine, I just call them Q1 and Q2, and he calls them here Q1 and Q2. And he is also using R for radius, and I'm using D for distance. So I believe he's actually going to use this as a radius, and in mine I'm using it as the distance between the charges. And so this is where our models kind of differ, but he does get, sensible results, which makes him think that his model is correct. Okay, so in this model, what he does is he is using this equation, and in this equation it's got Q1 and Q2, and so he's assuming that Q1 is elementary charge. So he is using elementary charge to plug into the Q1 and Q2, and he is using the classical electron radius for the radius term. So he's assuming a radius, it's a radius and not a distance between charges. So when he plugs in elementary charge and classical electron radius into this little equation, lo and behold, he gets the exact value of the mass of the electron. And so, he looks at this, we look at this, and we go, oh, this is good. He calculated the mass of the electron by plugging in some parameters that are associated with the electron, and he gets out the mass. So I just want to have a quick look here at the classical electron radius, okay? So the classical electron radius is a combination of fundamental physical quantities that define the length scale for problems involving an electron interacting with electromagnetic radiation, is what they see here. So what I want you to see here is that this is how they calculate the classical electron radius. So this calculation here, classical electron radius is, this will look familiar. This is 1 over 4 pi times permittivity of free space. This here is the Coulomb constant, and elementary charge squared, the mass of the electron, and speed of light squared are incorporated into this formula. And you get out something that has units of the meter, 2.81, etc., times 10 to the 15 meters, or 10 to the minus 15 meters, sorry. And so what I'm going to do here is I'm going to do the same thing that I did for all of my other formula. Is I'm going to convert from the domain of permittivity to the domain of permeability. So I'm going to write this formula in terms of the permeability of free space, knowing that this times this is equal to this. And so when you write it this way, you see that we have just recreated the formula that Robert Distinti used to, we just recreated this formula, which is, the inverse. So basically, if you swap the mass and the radius here, you get the formula that he used. These are the same formula, only, the mass and the radius are flipped. So he used the same formula to calculate the mass of the electron that was used, where the mass of the electron and the elementary charge was used to calculate the classical electron radius. So this is a little bit circular logic here. Not that there's anything wrong with that. It is, maybe you could call it a self-consistent system. And so, of course, you would expect this kind of logic to apply. But so it just makes it a little less remarkable that he came up with the mass of the electron using this formula, because the classical electron radius was actually derived from the inverse formula. Okay, so I just wanted to make that point clear, because I may in fact be doing the same thing in the future, only in a few minutes, only I'm going to be using different parameters for here, and I will have a reason why I'm using the parameters I'm using. And so, so this is the way Robert Distinti does it, and now I'm going to show you the way that I would like to do it. So in the previous video, I mentioned how I believed that nature didn't care about radius, and that any formula that we write regarding the underlying nature of matter that involves radius might not be getting to the root of the truth. And so, when you look at nature, when I look at nature, I see that nature cares about, not that it cares about anything, but that nature seems to be more about charge separation and boundary conditions. Okay, so when you look at, how atoms come together to make molecules, and how cells work, where you have charge separation on either side of the boundaries of the cell. So you've got boundary conditions and charge separation going on everywhere. And so I would like to find parameters that talk more about, boundary conditions and charge separation. And so this is where the Compton wavelength comes in. So there's another parameter in physics called Compton wavelength, and you can calculate the Compton wavelength from the Compton frequency, which I actually used in a previous video to show how you can use the electron to calculate the photoelectric effect, the frequency of the electron, to calculate the velocity created in the photoelectric effect. So I've used this before, but I've used the Compton frequency. So it's my opinion that the Compton frequency, although it is interpreted, well, let's just have a look here. I think I have a slide on that. Okay, so in mainstream, the Compton wavelength is a quantum mechanical property of a particle. Of course, everything is quantum mechanics. The Compton wavelength of a particle is equal to the wavelength of a photon whose energy is the same as the mass of that particle. So that's just a long way of saying the mass is used to derive the wavelength, and the mass is also used to derive the frequency. And so, and so that is what I think this particle is telling me. This is a schematic of a particle that has where the outer circumference is Compton wavelength. So Compton wavelength, in my opinion, isn't a wavelength at all. I believe that Compton wavelength could just as easily be the circumference of the circle, of a boundary condition of the circumference of a sphere of a certain size, and that the radius of that in this model here, in the yin-yang model, in the Ohm particle model, the radius of this boundary condition is exactly the same as charge separation. So I can take, so the Compton wavelength, which is really the Compton circumference, is one parameter in my system, and the Compton circumference, or the Ohm particle circumference divided by 2 pi is going to give the radius, which just happens to be charge separation. Okay, so that's why I like this model as opposed to Robert Distinti's model, because Robert Distinti's model is not showing any boundary condition. It's just showing the charges in motion. And of course, if these charges are in orbit, in motion around a central point, they are going to be creating a magnetic field, because that's what charges do when they move, if this is in fact a charge. Okay, if this is in fact a charge. And so I'm going to go back here, and so there are 2 charges in this model, and the question is what to assign these charges to. Robert Distinti uses the standard electric charge. He uses the standard value for charge. Okay, but I don't think, and this is my opinion, okay, I don't think that this can be elementary charge, that Q1 and Q2 can be elementary charge, because if this is, let's say this is an electron, I'm using this to model an electron, the electron is elementary charge. Okay, let's say we have, a bunch of charged particles in a field, and most of these are electrons, some of these are moving backwards, this would be a positron. But this is elementary charge, and this is elementary charge, and this is elementary charge, and so it doesn't make sense to me that Q1 and Q2 can be elementary charge. They have to be something else, in my opinion. And so this is where Planck charge comes in. And so here's how you calculate Planck charge in terms of the permittivity of free space, because charge, I believe, is more related to permittivity than permeability. But regardless, this is how you calculate Planck charge. This is actually reduced Planck charge. This is what we'll be using in my model. And so reduced Planck charge is the square root of epsilon 1, which is the permittivity of free space times 4 pi. This is reduced Planck's constant, and this is the speed of light. So this is how you calculate Planck charge, and Planck charge is what I believe Q1 and Q2 are. Okay, so I believe that the circumference of this circle is identical to standard Compton wavelength, and now I'm saying that Q1 and Q2 are in fact Planck charge and not elementary charge. And so let's see what happens when I plug this information into this equation here. So the other thing I want to point out here is that the Compton wavelength, which I don't believe is a wavelength, but it's circumference of a circle, but whatever this value is calculated using the mass of the particle, And so the Compton wavelength that I'm going to use is going to be the Compton wavelength of the electron, because I use the mass of the electron to calculate the wavelength. So this is the same circular logic that I showed you before that Robert Distinti was using. It's not really circular logic, it's a self-consistent system. So I'm building a system and it's self-consistent. So all of these parameters are related to each other. So some people might call it circular logic, but in reality it is a self-consistent system. In my opinion, that's how I see it. So here is my model of the electron. The Q1 and Q2 that plug into this equation here is this value that we just derived. The D parameter here is actually the reduced Compton wavelength, which isn't a wavelength at all. It is in fact the radius of this circle. So reduced Compton wavelength calculated using h bar is going to be 2 pi smaller than the circumference. So it's going to be circumference divided by 2 pi, which is the radius, which also happens to be the charge separation. So that is why I'm putting D in here. And then finally, we plug in the permeability parameter, which is really just a scaling factor, and it scales it to 7 orders of magnitude, and then we get the mass of the electron. And of course, that should be no surprise, because this equation here it uses the mass to calculate that distance. And so so this is circular logic, but it's also a self-consistent system, which interprets the way I like, which interprets in a way that I like, where I start with the radius of this, the boundary condition of this particle, and the charge separation of the charges that are in orbit around a central point. It's a binary system. And so these values all work together to create a self-consistent system. So these values here are really just describing this system here. And so the circumference is actually this value here. If I use h instead of h bar, it's going to give me the circumference of the circle. And so so this is what I'm doing, which is different than what Robert Distinti is doing. He's using classical electron radius, and he's using the elementary charge, standard elementary charge, and I'm using the Compton wavelength, or reduced Compton wavelength, which is the radius, which is also the charge separation, and coming up with the mass of the electron. And so so this actually interprets better than what Robert Distinti was doing, and this is closer to what nature does, because nature cares about charge separation and boundary conditions. And so this is my model of the electron. If you plug in the proton mass instead of the electron mass, you're going to get, this is going to interpret as a proton. The charge separation is going to be smaller, and the frequency is going to be faster, which is going to make the particle appear more massive. So really the massiveness of this particle is determined by the frequency of the spin. And the faster that this particle spins, the closer together these charges become. And the closer together these charges become, the faster this can spin. And so the faster it is actually this spin rate that determines the mass of the particle. And so this brings us full circle back to oscillation mechanics and modified unit analysis, where everything is converted to the frequency domain. Okay, all of the physics is done in the frequency domain, and there's an emphasis on cycles per second as opposed to radians per second. So I am working in the frequency domain exclusively, and so I think it's important to convert all of physics to the frequency domain. And so the Compton frequency of the electron, for example, is 1.2355, etc., times 10 to the 20 cycles per second. So these charges are spinning about this central point this many times per second. So as you can imagine, the Compton frequency of the electron, these charges spinning about this central point, are doing it very, very quickly. Here's the Compton frequency of the proton, and as you can see, it is 3 orders of magnitude faster than the Compton frequency of the electron. And so this object is spinning much faster. It's spinning much faster, but its charge separation is much smaller. The charge separation of the electron is in the order of 10 to the minus 13 meters. But the charge separation of the proton is in the order of 10 to the minus 16 meters. So the proton charge separation is much, much closer together than the electron, but it also is now able to spin much faster than the electron. And what you find is that the charge separation to frequency is going to produce a tangential velocity of the speed of light. Okay, so the electron charge separation of this entity is much bigger, but its frequency is much lower than that of the hypothetical proton, where the charge separation, where the distance between charges is much smaller, in the order of 10 to the minus 16 meters. Okay, so the electron spins slower, but its charges are farther apart, and the proton spins faster, and its charges are closer together. And the main reason for that is a very simple law of physics called the conservation of angular momentum. And so conservation of angular momentum causes the generalization of this, the Ohm particle, to have a tangential velocity of the speed of light, no matter what size it is. So it conspires to create the charge separation and the boundary condition such that the tangential velocity of this object, this bound object, these two are bound, so this bound object will have a tangential velocity of the speed of light. And this is the boundary condition. This is the escape velocity. This is the event horizon, if you want to call it that. It's not really an event horizon. It is more like a photon sphere. But the tangential velocity of this is, in fact, the speed of light, whether it is an electron or a proton or some other hypothetical particle, which I will talk about in my next video. So I guess that means I'll be back.